This is another classic demonstration and lab. Hydrates are ionic compounds that have water attached to them. That number of water can be anywhere from 0. I've even seen them to be up to 12. Consider them as little parasites. They're not part of the ionic compound. They're just in there. They're embedded in the crystal. So this experiment tries to figure out what is the formula of copper 2 sulfate. Now, you won't be doing this exact same experiment. You'll be doing one that's going to be similar to it. All right, so the question is copper 2 sulfate. How many waters are going to be attached to it? In other words, if we were to name it, this would be called copper 2 sulfate blank hydrate, and that blank is going to require a prefix. Now, the key concept here is that we're still dealing with mole relationships. So this means that for every 1 mole of copper 2 sulfate, we're going to have a certain number of moles of water. So let's see what happens in this experiment, and let's see how we can convert masses into a mole ratio. So step number 1, as always, is, even though I am using a nice electronic balance, some of you may be using a triple beam balance. I like the triple beam balances because you can take the mass to a longer decimal, to the thousands, but I needed to do this quickly, so I went with the electronic balance. So record this mass. This is the mass of just the crucible. So I have now added a certain amount of copper 2 sulfate. Notice it's blue. Does that mean that water's in it? Yes, it does. Will water always make hydrates blue? No, it doesn't. It can be any color. And the change can be any color. In this case, what we're going to be looking at is a change from blue to white. But I've seen it go from purple to blue, from white to white, from green to white. It can be anything. It's really kind of weird. Notice that the mass of the copper 2 sulfate and the crucible is 43.56. Knowing that, we can now figure out how much of the copper 2 sulfate hydrate with water we have to deal with. We'll do the math here in a few minutes. The setup is going to be similar to that of the copper 2 oxide. And once again, we've got a Bunsen burner. We have a ring stand. Now we're using a wire gauze because we want the evaporating dish. The evaporating dish, I may have called it a crucible earlier, the evaporating dish to sit on the wire gauze. Once again, we're looking for a cone within the cone, and the very tip of that inner blue cone is going to be the hottest part of the flame. That should be in contact with the wire gauze. So you will need to adjust your ring stand accordingly. So here we go. We're going to be very quickly doing this. This should take about 10 minutes, but with the magic of super speed, it can happen in about 13 seconds. All right. So we've conducted the experiment, and now we have an anhydrate. I did this twice in order to make sure that I had removed all of the water. The first time I did it for about 10 minutes, I let it cool down because just like in the copper 2 oxide lab, we need to be aware that ceramics have a tendency to absorb water, and that increases the mass a little bit. Not much, but a little bit. Enough to possibly influence your experiment. So I heated it up for 10 minutes. I let it cool down. I waited till it could rest comfortably in the palm of my hand. I massed it. I recorded that mass. I heated it up for another 10 minutes. I let it cool down, and I got the same mass. Yay! If I had gotten a different mass, then that would have told me that water was removed. Now the question would have been, have I removed all of the water? Well, there's only one way to find out, and that is by heating it up again, which would be a pain in the butt, but you have to do what you have to do. Okay, so how do we find this formula now from the information that we have? Evaporating dish was 40.27 grams. The evaporating dish plus copper sulfate plus water is 43.56. The evaporating dish plus just the copper 2 sulfate is 42.43 grams. Okay? So what do we do now? Well, we need to find the mass of the copper 2 sulfate, and we need to find the mass of the water. If we were to subtract these two numbers, I believe we'll get a difference of the copper 2 sulfate. So that's a mass of 2.16. That is just copper sulfate. All right, now we need the mass of just the water. Well, which of these three things have a difference of just water? Well, it's going to be this one and this one. See it? Evaporating dish, copper 2 sulfate, water, no water. So that's it. That's it. Now, what we need is a mole ratio. A mole ratio, which means these grams are useless to us. We're going to have to convert the grams to moles. What is the formula mass for copper 2 sulfate? So, 2.16 divided by 159.6. Okay, so we're going to do the same thing for water. I know the mass of water. 2 hydrogens, 1 oxygen, 18. Following our empirical formula rules, we have 2 moles, but that needs to be a whole number ratio, so we divide by the smallest mole. It's going to be 1, which is good. We were expecting 1, 2, 4.6. Well, it has to be 1 to something. So I'm a little off. I'm going to, normally in empirical formulas, we would have to multiply this probably by 2, but we can't do that. We're stuck. So we're just going to go with 1 to 5. So the answer is 1 to 5. Well, something went wrong. I don't really trust this balance scale because the answer is 1 to 7, and normally this experiment you're off by 1 water plus or minus. So I was expecting either 1 CuSO4 6 H2O or 1 CuSO4 8 H2O. So I'm a little off. I'll have to deal with it. But at least you get the idea. Now I want to show you one more thing. This is very interesting because remember, in order to make the hydrate become anhydrous, lose the water, what did we do? We added energy. It was an endothermic reaction. Watch what happens when I add the water back. That's steam. There's so much energy coming out that some of the excess water is converting to steam. So this proves a very interesting concept. This is a physical reaction. So when water is driven out, you have to add energy in. When water comes back in, then the energy has to come out.
It's hot.